Alright guys, so as I promised, I'd make another video and a little further explain the volumetric efficiency and some of these cycles in the engine, the dynamics of a running engine. So most engines have some type of throttle body or throttle bodies, and basically as the engine is running, it's trying to draw in air. There's a difference in pressures. I typically refer to these as a differential. I try not to use the word vacuum and pressure as much, even though it's a little more simpler. It's not quite really what's happening. So I'll use lower pressure, higher pressure, pressure differential between the two. Typically when I say vacuum, I'm typically referring to less than atmosphere. Atmosphere right now is, sea level is 14.7, 14.5, somewhere in there, pounds per square inch. So a typical running engine, if you put a vacuum gauge on it, some of you boosted guys will have a pressure and a vacuum gauge built in already. 18 pound or 18 inches of vacuum. It's your typical kind of running engine. You can do a lot of diagnosis with a vacuum gauge as well, but that's a whole nother subject. So what's creating that vacuum is the throttle valve shuts and the engine is still trying to draw in air, and it can't because you're restricting it by the throttle body being closed, like at idle. So that is reducing the volumetric efficiency of the engine. So efficiency meaning how well something is doing its job. Volume here, we're referring to the volume of air. How much air is getting in the engine compared to the size of the engine or the size of the cylinder. So as I mentioned earlier, let's say we had an 8-liter V8, huge, massive. That's 1 liter per cylinder. So if you got, 0.9 of it filled, that's 90% volumetric efficiency. Somewhere between 85, 90, 95 for some. That's typically where your modern street cars lie at as far as volumetric efficiency. You're going to lose some through the throttle body, through the curves, through past the injector nozzle. The valves themselves are the biggest restriction to air in the engine, but they're kind of necessary for the most part. So what makes the air come in the engine and what makes the air go out of the engine? Why do we have it and why is that important? So we all know we need air and fuel in an engine. We need to pump fuel into it, but it makes air on its own or brings air in on its own unless you have a turbo or a supercharger, of course. So the textbook or more common understanding and technically misunderstanding is the piston comes down and sucks in air kind of like a syringe, and then that gets compressed, spark, that's the power stroke, pushes the piston down, and then the exhaust valve opens, piston comes up and pushes all that stuff out. It's actually not how it works, at least not all the time. So there's a differentials in pressures and then velocities. Velocity meaning the speed, how fast things move, how fast things happen. It's actually a vector quantity. That's a whole nother subject we'll get into further later. So pressure and velocity are inversely proportionate. So that means as they change, as pressure goes up, velocity will go down to the equal amounts. So if you have 10 points of velocity and you have 10 points of pressure, pressure goes up by 5 to 15, velocity drops from 10 to 5. And I'll get into that a little bit later and why that's important and why some of you guys see cylinder number 6 on the VQs run lean and get hotter, and typically will be the point of failure for a lot of people, and I'll explain that also. So air does not come in with the piston going down. Air does not go out with the piston going up. Well, what the hell? How does that happen? So here's the thing. Let's start with the ignition and the combustion. So let's say you've already ran that cycle. Air and fuel is in the engine. It's being compressed. It's already there. Intake, exhaust valves are both shut. Spark plug fires just before top dead center. The pressure starts to build up. The piston comes up, goes past its dwell, starts coming back down. The pressure is immense. 250,000 PSI right there in that first little couple hundred thousandths as it drops down from the cylinder. That expanding gases in there push that piston down. That ultimately rotates the crank, and that's where we get torque from. The faster we move that torque, that's horsepower. It's a calculated figure. So that happens, piston comes down. Before it reaches the bottom, the exhaust valve opens. Now this is still under such high pressure and temperature. The exhaust gas goes shooting out of the exhaust port, even though the piston is dropping down. As this happens, it's going out very rapidly. So the velocity is very, very high. As that happens, the piston swoops back down and starts to come back up. The intake valve is also open. Intake and exhaust valve are open at the same time. And while this is happening, the piston is on its way up and air is coming in. Well, how? Well, pressure and pressure differentials. So as I mentioned earlier, velocity and pressure are inversely proportionate. So we got that exhaust gas coming out crazy fast, the speed of sound, actually. As it's pumping out of the exhaust port, it creates a low pressure area in the center by the spark plug with an overhead cam engine in the cylinder. And that actually draws in the fresher air coming in as the piston is coming up because of the exhaust port. The exhaust port is driving the intake port, not the piston. So as that's starting to come in, the exhaust valve eventually shuts first, then the piston's coming up, and then the intake valve shuts. Once the intake valve shuts, it starts compressing the air and fuel that has been trapped in the cylinder. That's the key to the whole thing, trapping air in the cylinder. You can have too much of that overlap period and you just blow air and fuel right out of the engine. If you have cats, they'll glow red. You're just wasting fuel at that point. Very inefficient at certain RPM bands. So you've trapped this air and fuel, intake valve shuts. Now the piston is compressing this air, ignition fires, and the piston comes back down and it starts all over again. So I mentioned volumetric efficiency. How much air actually got in the cylinder? Well, as we mentioned, it's the exhaust port that drives a lot of this. It's not the only factor. At certain RPMs the piston can, but that's usually at your idle and things like that. So with the exhaust port making such negative pressure or pressure differential inside the cylinder, under normal circumstances, you open the intake valve, you've got the air we have here, 14.7 psi, depending on your height above sea level. We've got 6 miles of air, or column, 6 miles or so high of just air waiting to be pushed in at 14 pounds of pressure. You take away pressure in the cylinder, and it just adds up to that much more, ramming the air in. And that's actually how engines work, not off the piston dropping. Now, cool thing here is, and I'll get into this one in the next video too, the exhaust is a lot of different things. Energy is a lot of different things. So energy can be sound, we can hear the exhaust. Energy can be heat, we can obviously feel that exhaust from the heat rise, and it has kinetic energy as well. It moves as a physical gas moving. All these things are important. The higher the temperature, the higher the velocity, the faster it's moving out, the better it's going to evacuate that cylinder, and we call that scavenging. So here's some cool stuff. So that makes a low pressure area into the cylinder, right? Well, with your header, if it's properly tuned, and I'll explain what that means later, as one pulse comes flying past the collector where the next tube, that we call it a primary tube, runs to the collector, it's going to create a low pressure area there, which is going to then draw on that next cylinder when it fires and help pull even more out. So now not only is the pressure in the cylinder being forced out, but the next exhaust pulse has helped sucking, if you would, that one out, and those in turn pull more intake air in. and it keeps repeating and repeating and repeating. That's called scavenging. We want to evacuate the cylinder of all the fuel that was not burned. Hopefully there's not much, but that does happen. It's not 100%. Engines are actually thermally very inefficient, but that's what happens. We're drawing that out. So if you properly design your header with the correct length, that will happen. There's also sound in there as well. Things move in a wave. Well, when that wave hits the collector, it's going to bounce back and go the other way. Well, when two waves meet each other, if one is down and one is up, they'll kind of meet in the middle and they cancel out. If both of the crest or the troughs meet each other, they'll amplify. So if one's here and one's here, it's going to go here, and that wave is stronger. And guess what? That's going to pull even more out of this cylinder. It's going to evacuate that even better. So at certain RPMs, you can tune your exhaust length and the diameter, the pipe size, that's important as well, to get the correct length of that wave, so at the right RPM, they can meet up, double themselves, and draw in the cylinder even harder. That's why your different diameter and lengths of headers move your power higher or lower in the RPM band, or widen it out altogether. Temperature plays a huge factor in that as well. This is moving at the speed of sound. The speed of sound changes based on the temperatures and the medium of which it's going through. All of that is dynamic. It's changing constantly, second by second by second, as the engine is running. So we got all this work just pulling and sucking, trying to get air out of the cylinder. Well, now we got to get it in the cylinder. Aside from the VHR guys, your throttle body is mainly important for that. You open the throttle body, air come in there through the manifold, and the intake manifold has its runners. Just like the primary tubes on the exit side, the runners are on the intake side, and they have a certain length and diameter just like they do, as well as a plenum area for the intake like the header has the collector. So as the air is coming in, super fast, just rushing in, the intake valve shuts, okay? And then all that air balls up at the valve, and then like a spring goes back the other way. When that happens, it goes back up toward the other air rushing in, it meets up, and then bounces back the other way again toward the valve. You tune your intake length and diameter for this wave to come down right as the intake valve is opening again, and now it's shoving itself more air in the cylinder. So you've got your exhaust tuned perfectly correctly, where it's sucking and pulling as much as possible at the correct RPM, while the intake is now running in as much as possible, and it's got some timing where it's doubling up itself with its wave pressure to push in even deeper, to push in even more air, and that's going to increase your volumetric efficiency. Here's the really cool thing about that too, and I can go into more detail with the plenum area as well. That plays a huge factor in your throttle response and so forth. But you do these things all together at a certain RPM band you tune for. You get your header length, your primaries, the correct length, correct diameter, the collector has to be the correct size, the intake port, the correct shape, the correct size, and when you get it just right and all these things line up together and they are assisting each other and everything works as a system for a narrow RPM band, you will exceed 100% volumetric efficiency. You will make boost. You will make boost naturally aspirated. You won't see that in the cylinder. I mean, you won't see that in your intake manifold because this is happening in the cylinder, not the intake. If you see pressure go up in the intake, you have what's called a reversion, where the air flows backwards and goes up the intake valve, which is something the VQs actually do from the factory. And I have a new product that is going to fix that with my new valves, full titanium valves, spin them as high as RPM as you can. But that's how you make boost naturally aspirated. 10%, 15, 20, 30% more air naturally aspirated, but it happens at a very narrow RPM band. Hope you guys learned something. You have any questions, fill it out below. I'm here to help.